All right, we're about to dive into a tiny two-letter word that reveals a huge secret about how our minds work. That word is not. And to show you exactly what I mean, I want you to try a little experiment with me right now.
And, yep, I'm willing to bet a big gray elephant just popped right into your head, didn't it? It's almost impossible to stop it. But this isn't just some fun little party trick.
No, this is actually a window into a massive puzzle in the world of psycholinguistics. That's the study of how our language and our brains are connected. This whole elephant problem thing, it shows us a really counterintuitive process that's happening inside our heads every single time we hear the word not.
Okay, so let's start at the beginning. Researchers have found that understanding a negative statement, something with a not in it, actually takes a little more brain power. There's a higher processing cost compared to a positive one. And the reason why, well, it takes us right back to that elephant.
So how in the world does our brain handle this? Well, one of the leading theories is called the two-step model. And it basically says our brain can't just jump straight to the negative meaning. Nope, it has to take a quick little detour through the positive version of the idea first.
So let's say you hear the sentence, zebras are not dotted. Your brain's first move is to process the core idea. Zebras are dotted. Seriously. For just a split second, it creates that image of a dotted zebra, and only then does it apply the not and reject that idea. That is the two-step process right there in action.
Now, things get even weirder when we start looking at double negatives, especially when we look across different languages. You'd think, right, that two nots would always cancel each other out to mean yes, but you'd be surprised. In some languages, like German, they use what's called double negation. Two negatives cancel out, just like in math class. Saying not nothing literally means something. But then you have languages like French or Spanish that use negative concord. Here, two negatives just make the no even stronger. Saying I don't know nothing really just means I don't know anything at all. I mean, these are two completely different ways of thinking.
And get this, here's a really fascinating twist. When scientists cooked up their own artificial languages and tried to teach them to people, they found that participants had a much easier time learning the negative concord system, the one where two nots just make a stronger no. It kind of suggests our brains might be naturally biased towards reinforcing a negative idea instead of canceling it out.
Okay, but what if I told you that understanding the word not goes way beyond just language? What if it's connected to something much more fundamental, much more physical in our brains? Because this is where the research gets absolutely mind-blowing.
Here it is, the big reveal. Brain scans show this incredibly deep link between understanding the word not and physically stopping yourself from doing something. When you process a command like do not touch, the part of your brain that physically puts the brakes on your hand, it actually lights up. Language is literally hitting your brain's brakes.
This is just a perfect example of something called the neural reuse hypothesis. The idea is basically that our brains are expert recyclers. So instead of building a whole new brain tool for an abstract concept like not, the brain just said, hey, you know what? Let's just repurpose this older, more basic tool we already have, the circuit for physical self-control.
So this is all fascinating stuff, right? But what does it all mean in the real world? Why does understanding how complicated not is actually matter? Well, it turns out it has some major implications, from how kids learn to how we communicate in clinical settings.
First, just think about kids. Learning to say no might seem simple, but really mastering all the complex grammar rules around negation, that's a long, long journey. In fact, research shows that even kids who are 11 or 12 years old are still fine-tuning these skills. It's a sign that our language systems are developing way into our teenage years.
This connection between not and our brain's brakes also has real-world importance, especially when we're communicating with people whose inhibitory control might work a bit differently. A great example of this is a pilot study that looked at how children with ADHD process negative commands.
And the results were pretty striking. It turns out that while all children were a little slower to respond to negative instructions, that delay, that extra processing cost of the word not, was significantly larger for the children in the ADHD group. This suggests that for some people, applying those mental brakes for negation just requires a little bit more effort.
So, look at how far we've come. We started with a simple party trick about an elephant, and we've ended up deep inside the architecture of the human brain, connecting our language directly to physical action.
So the big takeaway here is this. The word not isn't just a piece of grammar. It's a fundamental cognitive function.
Every time you use it, your brain is simulating a reality and then immediately rejecting it. And it's using the exact same neural tools that stop your body from moving. It's this incredible link between abstract thought and physical action.
Which, of course, leaves us with one last, huge question to think about. If a tiny, simple word like not is so deeply tangled up in our brain's physical wiring, what other parts of our language are out there secretly shaping the way we think?